Okay, so we've said that we've been doing some revision on force on moving charges, and so far we've looked at how electrons behave in a region of magnetic field. So we've discussed and said that in a region of magnetic field, as an electron enter in the region of magnetic field, it is acted upon by a force. Which direction of force is normal to both the direction of the charge and also the direction of the field. So this diagram, like I've said, it would have been better to indicate it in such a way that an electron comes, it follows a circular path. A uniform circular path has got a radius and therefore a center. So the force acts on this electron at 90 degrees at every point, pointing the electron towards the center of the what? The force pointing towards the center of that circular path. So we say that when this happens, there are two forces that are taking part here. There is the force due to the moving charges that we've just derived, and also there is the force due to the centripetal force. So the two forces are equal to each other. This one and this one, and then we simply, when you cancel V and V, make R the subject, you come up with something like that. Remember, I told you that charge can be given as the number of total charge can be the number of charges times the value of the basic or unit charge, which is E. So when you substitute Q with any E, you come up with this formula. Now that is the radius of the circular path described by a charge in a region of magnetic field. I repeat, this is the radius of the circular path described by the charge as it travels through the region of magnetic field. Is that okay? Okay, so all this I've been looking at, I've talked about it, yes. Yeah, this one, we've said that it is supposed to be NE. So it's supposed to be an N there. Alright, so let us have some examples. Of course, uh, when they give you the direction of electron, then the magnetic field, and they ask you to complete the diagram, it is as simple as showing that at every step, this electron is acted upon by a force whose direction points to the center of the circular path that is taken by this electron. That okay? So it's simply showing that if this is the direction of the electron in the region of magnetic field, it travels but undergoes acted upon by a force and then finally comes out like that. So we've talked about that. Then some applications, a straight wire of mass. So we have the mass, which is grams, which is same as 0.2 kilograms. And length 1.5 meters carries a current of 2 ampere. Suspended in midway by a uniform horizontal magnetic field B. What is the magnitude of the magnetic field? What is the magnitude of the magnetic? What is the magnitude of the magnetic field? So this one is suspended midway. If a wire is suspended by midway, this time there are two forces acting on this wire because it is not making a circular path as per the question, but instead suspended midway. That means the magnetic force acted on this wire is balanced by the weight of the wire. We can call this one the weight of the wire. So magnetic force is balanced by the weight of the wire. So magnetic force we said is BQV. The weight is M what? M times acceleration due to gravity. Okay, so magnetic force Oh, we said that the force exerted on a current carrying conductor, not a charge. This one is a current carrying conductor. The force is B, right? BQV is for the force exerted on moving charges. B is force exerted on a current carrying conductor. I won't add sine alpha because the two are at 90 degrees with each other. I mean the conductor and the magnetic field. So it's simply substituting Bi. The current is given as 2. The length of a conductor is given. The mass is 0.2. Acceleration due to gravity 0.981. So we can get the value for magnetic flux density. So this is what we have. Yeah, just substituting mg is equal to B. When you substitute, you can get your B as that. That okay? So a wire of radius, now here we are given the radius. The radius 0.2 centimeters, which we can write as 0.2 times 10 power negative 2 in meters. Here we are given density, which is 2000 kilograms per meter cubed, is placed in a uniform magnet in a magnetic field. If the wire carries a current of 500 amperes, what is the strength of the magnetic field? The strength of the magnetic field, they are asking for magnetic flux density that must be placed in so that it can float itself. So if this wire is placed in a magnetic field, that means there are two forces that have to balance each other. If it is to float, if the wire is to float in a region of magnetic field, automatically it is carrying current I, but it floats in a region of magnetic field. That means for it to float, there has to be a force balancing its weight, and that force is the magnetic force. So the magnetic force on a current carrying conductor, we said is B. Then the weight of this conductor is m times acceleration due to gravity. But from the information that we are given, mass is not given, but we know that mass is density times volume, not so? Density times volume, but also we know that volume can be cross-sectional area times length. So that we can say our magnetic force, which is equal to the weight, we say B is equal to the mass, which we said is density times the volume, which is cross-sectional area times length. Then we can say times acceleration due to gravity. Of course, the L will cancel. You remain with the area. How do we get the area? We know the radius. So area is pi r squared. Substitute the radius. So we have B I is equal to density times pi r squared times acceleration due to gravity. So the question is, are we given I? Yes. The density we have, the pi, you can substitute pi. The radius we have, the g we have. So you can get B in Tesla. That is the strength of the magnetic field. Is that okay? Can I get some feedback? Are you following? Yes. People are quiet. What is going on? maybe I need to give them rights to talk. But we have co-hosts. Uh, we have co-hosts. Co-hosts, you are supposed to do something for people to say something, or we even have hosts. Okay,
Sure, good afternoon.
good afternoon.
So I'm requesting for your pardon about that part of bill, the one you said this cost is equal to bill. I didn't understand it very well. The MG is equal to bill.
Uh-huh, another person.
Yes, Master. Good afternoon.
Good afternoon. Yes.
Master, thanks for this. Master, what I'm requesting workbook in the group.
Hmm?
I'm requesting you help us display this after the lesson. You help us with the workbook.
Okay. That is through Mr. Kaziba, but don't worry, we shall have the notes.
Yes, Master. Thank you.
We shall have, but for now, just pay attention so that you pick something. Someone who asked where F is equal to B comes from, this was the previous time we talked about the force on a current carrying conductor. We looked at it last time. And we said that uh, force on a current carrying conductor depends on some factors. Okay, it is slowing down. I think I can stop sharing, then I share again. Mm. Okay, so we said that force on a current carrying conductor depends on some factors. One of them is the strength of the magnetic field. Another one is the current flowing through the conductor. Another one is the length of a conductor. And another one we said is the sine of the angle between the conductor and the magnetic field. So when you combine these factors, you have B I L sine alpha. This alpha is the angle that is made between the conductor that carries current and also the direction of the magnetic field. So that alpha is the angle. In other words, we always have to resolve to get a component that is perpendicular to the direction of magnetic field. The component of either we choose to resolve B and get its component that is perpendicular to the current. Yeah, we resolve B and get a component that is perpendicular to the current. Yes, something like this. So this would be B sine theta. So that's how the sine theta comes in. But when you combine, if we are to substitute a constant of proportionality, this becomes Bi sine L, and we always let our K to be a 1, so that the force exerted on a current carrying conductor is B sine alpha. So that's where we got that formula from. Where alpha is 90 degrees, our force would be BIL, because sine of 90 is a 1. So that's where we got that formula from. Simply stating the factors that affect force exerted on a current carrying conductor, or simply force exerted on a conductor like a piece of wire that is carrying current in a particular direction. So we have another one, and we realize that from this experiment, we saw that once you have a rod that is placed along two rails, and then you have the rails between the two poles of a magnet that supply magnetic field, the rod starts rolling. That means that there is a force that is exerted on this rod in accordance to Fleming's left-hand rule. For those who missed, we saw the Fleming's left-hand rule. I'm not very good at fine art, but we saw that once you have a thumb using a left hand, you have a forefinger like that. I'm not very good at fine art. Then you have so this is how we actually come up with of course there are some other fingers, something like that. My fine art is not good at all. But you imagine having three fingers: the thumb, the forefinger, and the middle finger, pointing at 90 degrees to each other. Then automatically, the thumb gives you the direction of the force and also the motion. The first finger points in the direction of the field, and then this middle finger points in the direction of the current. So once you succeed in having the field and the current perpendicular to each other, automatically the force comes in. This is the field, and this is the force, which shows the direction of motion. So I'm saying automatically, that is how simple it is. And that force that sets in, that makes the rod to roll along the rails, its formula is Bi sine alpha. And we said where the current and the field are at 90 degrees to each other, then this sine of alpha is a 1, because alpha is 90 degrees. So that's why we've been writing our force as simply B, because the current and the field are at 90 degrees. So now let us apply to this question, which says, the diagram below represents a cylindrical aluminum bar, AB, resting on two horizontal aluminum rails, which can be connected to a battery AB. A magnetic field of 0.1 Tesla acts perpendicular to the paper. I told you our reference is always to the paper. If it is going inside the paper, we have a circle and a cross. Outside the paper, it is a circle and a dot. For those who were with us in the first lesson, you learned this. Okay, so we shall continue. In what direction will AB move if the current moves from A to B, applying Fleming's left-hand rule? So what happens if the current, now this one I think I have to demonstrate it somehow. I don't know whether you can set me first stop sharing and then see if you can really see this. So we have something like this. I'm reminding us of the Fleming's left-hand rule. We know that if this points in the direction of the current, the thumb points in the direction of the force, then the forefinger, the direction of the magnetic field. So note that every time there is current at 90 degrees with a magnetic field, a force automatically sets in. And once the direction of the current is reversed, check this. If the direction of the current is reversed, say if it was, for example, here you can see to which direction, to that direction. If you change the direction of the current, but the direction of the field remains fixed, the field remains coming that side, but the current has changed to point the other direction. Do you realize that the force changes? Previously, it was acting upwards. Now it is acting downwards. So that means if it is a road, if it is a road connected, it will either move to one direction or to the other direction, depending on the direction of the current. So when the current is reversed, even the direction of the road is reversed or changes the because because the direction of the field or the motion, no, the direction of the motion of the force depends on the direction of the current. So we've maintained the field, but we've just reversed the current. So the force which was originally acting upwards, changing the current, maintaining the field, now points downwards. So that's what that question has been trying to ask. But at school, I think you'll have uh, a real demonstration of that simple explanation. That okay?
It is okay, sir.
Okay, so now let me continue and share. Okay, thank you so much. I was sharing the work for these questions. We try them out. I mean, we're still going through the examples. So this one, I've just said that a magnetic field of flux density that acts perpendicularly to the paper. When they say perpendicularly to the paper, perpendicularly into, this was supposed to be into the paper, then you would have something like that. And of course, it's like having, though this is two-dimensional, we write this one to indicate that it was actually going inside. In two-dimension doesn't come out so well, because now if this is the direction of the current and also the direction of the field, we have to show that the force is moving perpendicular to both the field and the current. But anyway, let's say um, so in what direction will AB move if the current moves from A to B? When you apply Fleming's left-hand rule, you'll come up with that direction towards the right. And when the current is reversed, it will be towards the left, applying Fleming's left-hand rule. This one I've said that you'll get it when you at your school, when teacher demonstrates it physically, you'll see how the direction comes about. So here they are saying that calculate the angle, the angle to the horizontal to which the rails must be tilted to keep AB stationary if its mass is that. Now here we have the mass 0.5 grams, which we can have at 0.5 times 10 power negative 3 kilograms. Okay. So we are saying that our mass is 0.5, 10 power negative 3 kilograms. The current is given as 4.0 ampere, and the direction of the field remains unchanged. So we have the diagram like this, but remember, that if this rod is to be maintained stationary, if the rod is to be maintained stationary, then the force exerted on the rod must counterbalance the weight of the rod. The magnetic force must equal to the weight of the rod. So, this time, the rails are tilted through an angle theta. So if the rails are tilted through an angle theta and the rod is acted upon by a force, which we call the beam, that means we shall have to resolve. If this angle is theta, look at this. I hope you've done resolving. You should have done resolving. If I draw this, from what you learned in mechanics, if that angle is theta, this angle is also theta. So if I'm to resolve mg, if I'm to resolve mg along the rails, so this would be mg sine theta, and this would be mg cos theta. But we're interested in mg sine theta because it is the component that balances with the magnetic force. So that would be B equals mg sine theta. That okay? They are asking for the angle. A bill was given as B was given as 0.1 Tesla. So our B, let me write it here, 0.1 Tesla. So just substituting 0.1, the current was 4. I don't know the length. Did they give us the length or the mass? Perpendicular on it, okay. Times length equals the mass, I know it, and the G. Okay, we are looking for the angle theta. I'm checking if in the question I gave the length. Okay. Did I give the length 5 times 10? Okay, seems okay. We put it here. Excuse me. So this was our diagram. So if the length is given, the magnetic flux density, the current, the length, m, g, then we can get theta. We can always get theta. I don't know why I didn't include the length in the question, but in the working, it is there. That okay? Yeah, it is, the length is there. So you can always get the value of theta. So, but what I've seen, what we've worked out here is very simple. Remember, for the rails or for the rod to move, if this is my rod, if these are my two rails, excuse me, if these are my two rails, and then I have a rod like that, this rod moves along the rail because of the force exerted on this rod. The rod is carrying current, which I can call I, and this current is perpendicular to that. This current is perpendicular to the direction of the magnetic field, which we choose to represent as a circle and a dot to show that this magnetic field was actually entering into the paper. Entering into the paper, and the current is cutting it at 90 degrees. That means the current and the magnetic field are meeting at 90 degrees, which creates a force that makes this rail to move. Why? Because these are connected to a battery, the source of current. So here we have a case where the rails, these rails are tilted through an angle theta. That means for the rod to move like that, the magnetic force should counterbalance or should balance the component of the weight which is along the rails. So that's why we had to resolve this. If you maintain this line, the angle theta, this case, this angle theta is the same as that angle theta. And if you want to resolve along the rails, then mg along the rail would be mg sine what? Sine theta. So it is that mg sine theta that we equate to the magnetic force. And we said where you have, if you have mass, you have G, you have B, I, L, you can get the value of theta as per what the question requires. Okay, so that is it. So we have some revision questions. The force per unit length. Okay, this one is also a very common question. We may go through it. A current of 5 ampere flows through a straight wire in uniform magnetic flux density. Magnetic flux density, which is 2 times 10 power negative 3 Tesla. Calculate the force per unit length. Now, if force is given as BIL sine alpha, if I divide both sides by L by L. So that means F over L is equal to BI sine alpha. Now, force over L is what we term to as force per unit length. Force per unit length. So force per unit length is always given as magnetic flux density times the current times sine alpha. In case alpha is 90 degrees, then this force per unit length is given as simply magnetic flux density times the current. So yeah, that's what we have for this question. You can take notes. That okay? Is that okay?
It is okay, sir.
Calculate the force per unit length. So here, if the current is given as 5 ampere, and then the magnetic flux density is 2 times 10 power negative 3 Tesla, force per unit length is given as BIL. When they said when the wire is perpendicular to the magnetic field, it means sine alpha is 1 because alpha or theta is 90. So we can always get force per unit length just multiply 5 times 2 times 10 power negative 3. And then you get your answer as the force per unity. Force per unit.
Yeah.
Then inclined at 9. What happens if the conductor, remember the conductor is one that carries current. If it is inclined at 30 degrees to the direction of the magnetic field, then our force, which is BIL sine theta, you divide by L, you get force per unit length is BI sine theta. So that means it's a matter of substituting B, 2 times 10 power negative 3, the current, then the sine of 30 degrees, so you can get your answer. You can get your answer. This is what we have, as simple as that. So we have this one. A long solenoid has 100 turns, 100 turns in 1 centimeter, and a current I. An electron moves within the solenoid in a circle of radius. Now, when they say an electron moves in a circle of radius, what comes into your mind? Do you remember this formula? Where have I put it? Where have I put it? Do you remember this formula? When an electron describe a circular path, we derived that formula. But before we go into that, let us try to analyze the question. Along solenoid, number of turns. Number of turns, we call it capital N, is 100 in 1 centimeter. It carries a current of, are we given the current? I've not seen it so far. An electron moves within a solenoid in a circle of radius 2.3 converted to meters, perpendicular to the solenoid axis. The speed of the electron is given as 0.04 What is the speed of light? Times c is the speed of light. So what is the speed of light? Is it 3 times 10 power 8?
Yes.
So that's the speed of an electron. Find the current I. Okay. So, let me try to make this one simpler for you. We've talked about the magnetic flux. Of course, when we talk about a solenoid, then we talk about magnetic flux. So, magnetic flux of a solenoid, this one is NBL. Okay. Now, this one will require looking at the magnetic flux, magnetic flux density of a solenoid. When electron enters the center. Okay, this we shall see it. Let me skip this question because it requires another application whose whose knowledge is in the next sub chapters. So we can skip that for now. We can skip this for now. Magnetic flux density in the center or at the ends of a solenoid. That we shall look at it later. Okay, so let me see. Maybe this one, item 3. We can figure it out. A conductor carries a current of that at right angles to the magnetic field of flux density that if the length of a conductor is given, the force acting on a conductor can be given. This is what we have looked at. What is the force when the conductor makes an angle 45 degrees? That one we have looked at. It's a matter of substitution. Now still this one, a straight horizontal rod X of mass that and length that is placed in a uniform magnetic field. We looked at this, that when a straight conductor is placed in a region of magnetic field, to balance horizontally, the magnetic force balances the weight of the conductor. You know magnetic force is B, the weight of the conductor is mg. Sign, it's a matter of substitution. Matter of substitution. Okay. Okay, so these are basically questions for you to try out. They are not different from what we've been looking at. Horizontal, still we see the application of B is equal to mg. There you need to know that the conductor was held stationary in a region of magnetic field. So the magnetic force was balancing the weight of the conductor. Now here we have two springs. Let me see. Okay, so we have 13.0 gram wire of length. That one is suspended by a pair of flexible leads in a uniform magnetic field of that. What are the magnetic fields? So maybe we can have a look at this one, but the application still remains the same because we have a wire of the mass, which is 0. Okay, the mass of this wire is 13.0, which we can convert to kilograms by multiplying by 10 power negative 3. Its length is given as 62.0, which we can convert to meters. Is suspended by a pair of flexible leads. Now for this wire to balance, also we know. In fact, the rod we are talking about is this one. The X mean that there was a magnetic field that was entering into the paper in the region of magnetic field, and therefore magnetic field and current were crossing at 90 degrees. That's why you have theta as 90 degrees here. So you will balance the magnetic force, balance it with the weight. Magnetic force, which is B, sine 90 is 1. The weight of the rod is m times acceleration due to gravity. So the magnetic flux density, you have it from the question. They're asking for what? The length you have it, the mass you have it, you can get the current. You can get the current. That okay? So we're just having very many examples. I'm just taking us through the very many examples that we have.
Excuse me, teacher.
Yes?
So, oh, no, I've realized my mistake. I was going to ask about the angle, but then I've seen that it is 90. So it's fine. You
Yes,
can
90
continue.
degrees. 90 degrees. So when you see a conductor, every time you see this, and then you have a conductor, just know that this was going inside and this one across. So inside and across, that's 90 degrees. That's 90 degrees.
Okay.
Okay, so the current is to the right. Okay, all these ones applications of what we've just seen. They are just very many examples. They're just very many examples. Even this one, they're just very many examples. Now let us focus so much on the torque exerted on a rectangular coil. The torque exerted on a rectangular coil. I want us to share something here. Let me share something that is clear. Let me share something that is clearer. I think I have a PowerPoint somewhere.
Excuse me.
Yes?
So some people in the chat are saying that your volume is very low.
Oh,
Yeah.
okay. Got let me increase on the volume. That's fine.
And some people are saying that you're too fast.
Okay, thank you so much. We can continue. Thank you for the patience. So let us continue with our application. Now, this is torque. I hope you learned torque is simply force times perpendicular distance. Not so. When you talk about a body, when you talk about a body, let's say it's some kind of a rod. Then you have a force applied onto that body. Say that is the force. Then what happens? So let's say we have a particular turning point. That this force rotates a body through a turning point. Then the force exerted can be the product of the force and the perpendicular distance can be the torque. But now we are applying the same knowledge here. I know you've ever interacted or you've come across that torque. So, which is force times perpendicular distance. But in this case, maybe to emphasize more, you've balanced rods, yeah? You must have balanced rods given a turning point. Then you have a force. Just giving an example. You have a force, and then you have a turning point, and then you have a distance. And so, sometimes you say moment of a force, or you can say a torque, which is the force times the perpendicular distance. So we're just applying. You know that when you have your conductor in form of a coil, this time the conductor is in form of a what? A rectangular coil. Then you choose to apply a force on one side and a force on the other. A force on one side, then and a force on the other, which creates a couple. You know a couple, two forces that are acting on a body on either sides for which the body rotates. So if these are, we call it F1, we call this one F2. These are two forces acting on a body that makes it to do what? That makes it rotate, assuming that these forces act in such a way that each force, this is the direction of the magnetic field, if this is the direction of the magnetic field, the forces are acting in such a way that they are at 90 degrees with the direction of the magnetic field. This is 90 degrees. Also, this one is 90 degrees. So, let me consider my rectangular frame of wire to be X, Y, Z. Okay, W, X, Y, Z as my rectangular frame of wire. You know that a force exerted on this rectangular frame of wire is given as, it remains a current carrying conductor. It is a flame of wire, but it carries current I. Remember I told you that in a coil, you can have something like that for whichever number of turns, but they carry current in and out, current in and current out. But this time, it can be a rectangular coil. It can be a rectangular coil of that format that carries current in and out. So for us, for simple demonstration purpose, we pick out just one rectangular kind of arrangement. Let's say it carries current moving upwards and current coming downwards, something like that. So when current is moving upwards, exerted upon when current moves upwards, current meets the magnetic field at 90 degrees, the force is exerted in a direction like we've seen or like we shall see. So that means, and on the other side of the coil, this is safe. If you are looking at this side of the coil, current is moving upwards. Then the force is moving to, no, the current is moving upwards, then the field is moving to the right. When you apply the Fleming's left-hand rule, the force exerted on this wire will be such that it takes on the other direction. Like I said, this, you'll visualize it with your teacher at school. Now, what happens when current comes back? When current is coming back, maintaining the direction of the field. I told you when current reverses in direction, the force also reverses its direction. The force which was moving the other side now comes this side. So something interesting that happens now is that the two forces constitute a couple. The two forces constitute a couple. They make this coil, this rectangular coil, to rotate. They make this rectangular coil to do what? To rotate. So as the coil rotates, we want to compute the torque of this coil. Of course, we know the force which is given us, the B times the I times the L, at every point we see that the current and the field are at 90 degrees. So we don't need the sine, we don't need the sine theta part because sine of 90 is a 1. But the question is, torque is that force times the perpendicular distance. Now, if we let L to be the length of the coil, let's say, okay, if we let W, this was X, Y, this was Y. If we let this to be the width and then this to be the length, if we let A to be the width and then B to be the length of the coil, our torque, which is the force times the distance, the perpendicular distance, let me use red, it might be more visible. So the torque, which is going to be the force, which is B times I times the length, then times the perpendicular distance. So the length, can be A, and then the perpendicular distance can be, length of the coil can be B. Let's say the length of the coil is B and the perpendicular distance is A. Just a matter of substitution, the perpendicular distance is A. That means my torque will be B times I. The length is B, the length of the coil, times A, which is the perpendicular distance. But we know that these are dimensions of the coil, B times A, which gives us the area of the coil, so that torque can be Bi times the area of the coil. As simple as that. So the formula for the torque exerted on a coil is given as the magnetic flux density times the current through the coil times the area of the coil. So this is the formula. So we've said that, where does it come from? If I have magnetic flux density, or simply the magnetic field, of course, meeting the conductor at 90 degrees, such that the current and the magnetic field are at 90 degrees, then a force will be created, which force will be perpendicular to both the magnetic field and the current. Now, when current reverses direction, that force also reverses direction. It was formerly following that path. Now it is coming towards me. Now, the two forces exerted on this rectangular coil constitute a couple. So they cause the coil to rotate about the axis of the coil. So if I take the axis of the coil to be, let me say the axis of the coil is this. So the coil will have to rotate in a particular direction, say clockwise for this case. So as a coil rotates, we can calculate the torque exerted on this coil, and torque is force times the perpendicular distance. The force exerted on a conductor, we said, is the same as BIL, B-I-L. We are not adding sine theta because the field and the current are at 90 degrees. So it is simply BIL times the perpendicular distance. So if we take the length of the conductor to be B, the length of a conductor to be B, and then the perpendicular distance to be A, to be A, which is the width of the coil, then we can say that our torque is equal to B times I, the length of the coil, times the perpendicular distance, which constitutes the area of the coil, because we see that B times A is the area of the coil. So the torque exerted on a coil is actually given as BIA. Now, all together. Things are becoming more complicated.
Teacher, yes.
Don't worry. Always the first time becomes a bit harder, but when you read through, another time you'll come across this, you realize it makes more sense anytime another person talks about it, or when you read about it, it will start making more sense. But don't worry.
But then, teacher, my question is,
Mm,
I'm wondering how that angle is becoming 90. Like, okay, in the 90s, we've been drawing
mm.
that is not 90, or you're just assuming it to be 90.
I'm not assuming it.
Mhm.
Let me see if I can share. Okay, we can visualize it. Let me share this. So this is actually what we have. Hope you can see. This is actually what I've been demonstrating. Yeah? And this is what happens in a moving coil galvanometer. In O level, if you have ever seen a galvanometer, this is what happens inside a galvanometer. Inside a galvanometer. So there are two powerful magnets, which we can call sides, powerful magnets, side north pole and south pole. Then inside is a rectangular piece of coil. So the magnetic fields are running from north towards south, and the current is moving through the coil like this. So let's say, do you realize or do you notice that the angle between the magnetic field and the current is 90 degrees? So when the angle between the magnetic field and the current is 90 degrees, it makes this coil to experience a force, that force which we can see. And that force is also perpendicular to both the magnetic field and the current. But when the current is moving through and coming back like this, the direction of the force now changes to come towards me. So it creates a couple. A couple. What's a couple? Two forces acting in opposite direction on a body, not so? So it creates a couple which makes this coil to rotate through a particular direction. So this diagram can bring out a picture somehow. Is that okay? That actually, the Fleming's left-hand rule is in full operation here. The thumb, which points in the direction of the force. We have the magnetic field. The forefinger points in the direction of the magnetic field, and then the middle finger, which points in the direction of the current. In the direction of the current. So that's actually what we have. But what I can say, I've tried to make it a bit simpler. So let me have it here on an empty page so that we can try to get it better. Okay, we said that a coil can be a plain circular coil, but a coil can be a piece of wire, just like a solenoid, just a piece of wire, and then you make turns into it, then connect it to a voltage. It creates a solenoid. So it can be one turn, or it can be very many turns, depending on what you want to make it into. So similarly, you can have a coil in terms of a rectangle like that. So that's one turn. Current goes in through the coil, and then current comes back through the what? Through the coil. But you can choose to have it in more than one turn. You can have it like that. Say rectangular coil, but with more than one turn. So still current will go in and then come back. That okay? So for demonstration purposes, we pick out just a rectangle. Just pick out a rectangle and we say, if this is my rectangle, of course I know that there will be current coming in, and on the other side, current coming out. So let's say that current is meeting the magnetic field. If this coil is placed in the region of magnetic field, such that on one side there is the north pole, another side there is a what? A south pole, then that means there will be a region of magnetic field from the north pole to the south pole. So every time there is a magnetic field cutting current at 90 degrees, a perpendicular force to both the magnetic field and the current is expected. So this force acts in such a direction that if current is moving upwards, applying Fleming's left-hand rule, then it will move. This coil will move to the other side. I want to. And the coil reverses direction. I mean, it continues to turn when current reverses direction. So this is a force and this is a force. So the two sides experience two equal but opposite forces. So that force experienced by a coil is given as Bi times L. Now, note here that the angle between the current and the magnetic field is 90 degrees. Is 90 what?